Testing. 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 All right, welcome to another stream. Today, we are going to be answering the question, what is the best GPU for deep learning? So this is a article on Tim Dettmers' blog. Tim Dettmers is a researcher, engineer who really knows hardware. He's published a couple different papers, especially in the field of quantization. But yeah, this guy definitely knows his GPUs and his hardware, so I think this article should provide all the context we need to answer this question. So up here I have pulled up in my terminal here, I have the GPU that is on this computer. This computer has a the NVIDIA SMI, which is the command that will tell you what GPU you have. You can also run this on Linux. This is a Anaconda prompt, kind of like a pseudo Linux that you can run on Windows. But this is a 3090 GPU, which has 24 gigs. And yeah, you can see we're barely using it right now because the only thing we're using it for is this monitor and then maybe OBS, I guess. But yeah, I know this has been a favorite question. People keep asking this question over and over again. So hopefully this answers. All right. Deep learning is a field with intense computational requirements, and your choice of GPU will fundamentally determine your deep learning experience. But what features are important if you want to buy a new one? The RAM cores, the Tensor cores, the caches. These are all different parts of a GPU. The cost efficiency. Blog will post into these questions, tackle common misconceptions, and give you an intuitive understanding. All right. The new Ampere series of GPUs from NVIDIA. So NVIDIA, there's different, basically, it comes down to like the releases, right? So you can kind of think of it as NVIDIA Ampere. They probably have an image that kind of shows you the position over the years, I guess. I was looking for. But basically they kind of like have different names for the different batches of GPUs that they release over the years. And I guess Ampere is the most. What makes GPUs fast? What is unique about the RTX? Overview. First, explain what makes GPU fast. CPUs versus GPUs, tensor cores, memory bandwidth, and the memory hierarchy of GPUs, how these relate to deep learning performance. So CPU is what's in the middle of your motherboard, and all computers have this, and for a long time, like this is what's Intel versus AMD, right, has been kind of the classic CPU trade-off, but GPUs are graphics processing units. So these are what you train on the GPU. The CPU kind of just generically makes your computer fast, but the GPU is what really allows you to train deep learning. Have here a link to what makes GPUs well suited to deep learning. And this is really the meat of it here, is that they are efficient for matrix multiplication and convolution. right? So GPUs were originally used for graphics, right? So whenever you're doing graphics, you have these little shader programs, and you have to run these tiny little shader programs to calculate what every value at every single pixel is very quickly. And those are relatively simple, right? They're just kind of multiplication, so you just have to do a bunch of multiplications at the same time. That's what GPUs are about. Versus a CPU is doing something that is potentially more complicated than a multiplication, but doing a lot of different things in as fast as time as possible. Okay, so I like this analogy here as a CPU is a Ferrari and a GPU is a big truck. The CPU, Ferrari, can fetch some memory packages in your RAM quickly, while the GPU, big truck, is slower in doing that, which is latency, right? Latency just means slowness. It means the time from when you say you want to do something to the time to when it's done takes a long time. That's what latency means. The CPU needs to go back and forth many times to do its job, while the GPU can fetch much more memory at once. Right, so basically the GPU is doing a bunch of things at the same time at a slower rate, versus the CPU does a lot of small things at a much faster time. The best CPUs have about 50 gigabytes per second, while the best GPUs have about 750 gigabytes per second. The advantage of the GPU is we can have a small pack of registers for every processing unit, which has many. Thus, we can have in total a lot of register memory, which is very small and thus very fast. This leads to the aggregate GPU register sizes being more than 30 times larger compared to the CPUs, still twice as fast. So he's introducing kind of different types of memory here, right? L1 cache is another type of memory, right? Cache is the French word for caché, which means just hidden, which is basically like a little store, right? So cache is a word for somewhere like a little bank of memory where you kind of put intermediate results really quick. Compiler tools. Store a lot of data in your L1 caches and register files on GPUs to reuse convolution and matrix files. Yeah, so when you're actually training on a GPU, right, the actual memory, or like the size of your model is going to, the size of the model you can train is going to depend on the memory of your GPU. If you have a GPU with 8 gigs, you're going to be able to train much smaller models than a GPU with 20 gigs, right? And eventually, especially with these big models like GPT-3 and any of those big foundational models, the memory size of that model is so big that sometimes you can't even fit it on small consumer GPUs. So he will probably go into that further in this article, but that is kind of one of the big decision points when you're purchasing a GPU for deep learning is, am I going to be trying to train big models with this GPU, or am I okay with a smaller memory GPU, right? And really, the only trade-off there is the big memory GPUs are going to cost more money, but it could be something important, especially if you're working in vision, where computer vision tends to have bigger models just because images are just kind of bigger to deal with. So that's something to think about. Talks about tensor cores. Tim here says tensor cores are the most important, followed by memory bandwidth, cache hierarchy, and then the flops. Floating point operations per second. That's what flops mean. Okay. Tensor cores are tiny cores that perform very efficient matrix multiplication, right? So a CPU has maybe 8 cores or like 16 cores or 24 cores, right? So they're the actual little atomic unit that is performing the operation. And GPUs also have cores. They just have a larger amount of much smaller cores, and that's what they call here tensor cores. fact, they are so powerful that I do not recommend any GPUs that do not have Tensor. Here I will show you a simple example of A times B equals C. So he's multiplying two matrices here, A and B, to get a third matrix, C. Matrices have size 32 by 32. Okay, so this is a 2 by 2 matrix. And tensor is just a mathematical term for a n-dimensional matrix, if you want to think of it that way. So you have one-dimensional number, it's just a number. Then you have two dimensions is a vector. You have more dimensions, right? Two-dimensional matrix, three-dimensional matrix, four-dimensional matrix, and then an arbitrary dimensional matrix is often called a tensor, and that's where tensor cores come from. That's where tensor flow comes from. It's the same thing. Let's see if we can get a better definition. Tensor that describes a multilinear relationship between... Wow, what a terrible definition. Definition as multidimensional array. So this is, I think this is the better. A tensor may be represented as a multidimensional array. I think just as a vector in an n-dimensional space can be represented with a one-dimensional array, any tensor with respects to a basis is represented by a multidimensional array. I think this is the better definition. Okay. Processor runs at 1 gigahertz, it can do 10 to the 9 cycles per second, right? So 1 gigahertz, right? Hertz is a unit of time measurement, right? So 1 hertz is 1 time per second. 1 gigahertz, right? It's like a gigabyte, right? Giga just kind of tells you that there's 10 to the 9 of that. So there's 10 to the 9 cycles per second. So if you think of your little CPU as like a little heart that's beating inside your computer, it's beating at 10 to the 9 cycles per second. So that just goes to show you, like, computers are ridiculously fast. It's doing a huge amount of little heartbeats per second. Latency timings. Global memory access. Okay, so it takes about 380 cycles to load anything from the global memory. It takes about 200 cycles to load anything from the L2 cache, which is probably slightly further away from the L1 cache, which is the kind of closest one to the little tensor core. And the L1 cache is only 34 cycles away, which seems like a lot of cycles, but remember, if there's 10 to the 9 cycles per second, 34 cycles is almost nothing. We're talking like nanoseconds. Probably less than that. A fused multiplication and addition, right? Multiplying two matrices, A times B, and then adding a third matrix, right? And this is basically the core of all deep learning, right? A fully connected neural net, at the end of the day, the operation that you're doing is multiplying the weight matrix times the input and then adding the bias, right? There's weights and biases are the main parameters inside a neural net. And that's basically what it is. It's a weight times the input plus the bias equals the output. So you're performing exactly this, a fused multiplication and addition. And that only takes 4 cycles. And then a tensor core matrix multiply only takes 1 cycle. Okay. So that's giving you an idea of kind of like what the different atomic units are. So I think the core thing, riffing on my making terrible puns, but the important thing to realize here is that accessing things from memory, right? Like let's say you have to load a new batch of data into your GPU to perform your matrix multiply, right? That's going to take 380 times longer than the multiply. So really what takes long, or what is the weakest link in the chain, the slowest part of this entire process, is loading things from memory into the GPU and then the actual matrix multiplies are actually pretty fast. Each operation is always performed by a pack of 32 threads. This pack is termed a warp of threads. Okay, so that's kind of like you have a murder of crows. I guess you have a warp of threads. Threads within a warp have to wait for each other. All memory operations are optimized for warps. Loading from global memory, right? So the slowest one here happens at a granularity of 32 times 4 bytes or 32 floats. Exactly one float for each thread in a warp, right? A float is basically a number that has decimal points, and an int would be a number that is just no decimal point, and the 32 basically is bytes, which is the actual atomic unit of like memory storage in computers. We can have up to 32 warps in a streaming multiprocessor, the GPU equivalent of a CPU. The resources of a streaming multiprocessor are divided among all active warps. For this small 32 by 32 matrix multiply, we use about 8 streaming multiprocessors, which is about 10% of a RTX 3090. Okay, so this is actually the GPU that we have on this computer. So roughly 10% of the GPU we have is going to be used for the 32 by 32. While the following example roughly follows sequence, please note that these are very simplified. Okay, that's fine. Matrix multiplication without tensor cores, and then matrix multiplication with tensor cores. Okay. So we're still doing this A times B equals C, which is still just a tensor core matrix multiply, right? You're not doing the addition part yet. You're just doing the multiplication part. Each matrix is of size 32 by 32. Okay. We want to load memory that we repeatedly access into a shared memory because its latency is about 5 times slower, right? So basically, you have this hierarchy of memory, right? You have memory that's closer to the tensor cores, then slightly further away from the tensor cores, and even more further away, right? And the further away the memory is from these tensor cores, the faster or the slower it's going to take to load it and perform that matrix multiply. So a huge part of GPU optimization when it comes to speed is basically like being clever about, okay, when do we take things from this L2 cache and put it in the L1 cache? And when do we take things from the global memory axis and put it into the L2 cache? So here they're talking about the latency, right? 200 cycles versus 34 cycles is they're basically saying, we want to take the stuff that's here in the L2 and put it in the L1. Memory block in shared memory is often referred to as a memory tile, or just a memory, or just a tile. Okay. Loading 2 in shared memory tiles can happen in parallel by using 2 times 32 warps. So due to parallelization, we only need to do a single sequential load from global to shared memory, which takes 200 cycles. Okay. Do the matrix multiplication, we now need to load a vector of 32 numbers from a shared memory A and shared memory B to perform the fuse, multiply, and accumulate. So this is the matrix multiply followed by an add, right? So multiply is the multiplication, and then accumulate, you're adding that, the C here. A times B plus C. And I guess the shorthand for that is FFMA. And then you store the final outputs in register C, which is basically just another kind of memory little tile. Okay. So you multiply this all out, you're spending 200 cycles to load stuff from the global memory. Then you're spending 34 cycles to load it into the L1 cache. Then you're spending 4 cycles to actually do the multiply and add for a total of 504 cycles. So cycles are basically, right, just a measure of time, right? And your GPU is going to have a clock rate, and that's going to be how many cycles per second it can do. So 10 to the 9 cycles per second, and this matrix multiply takes 504 cycles. It's still extremely fast, right? We're still talking basically nanoseconds. Right. Now let's do the same thing with tensor cores. So with tensor cores, we can perform a 4x4 in 1 cycle. So they're still going to have to load it from memory, so they're still going to spend 200 cycles loading from memory. Okay, but then they don't have to do, there's no 8 times the 34 here, you see? It's only 34. And what is the reason for that? Okay. So without the tensor cores, you'd have to perform 34. You'd have to basically load from the global memory to the L1 34 times, or 8 times, right? Because you have to load it, then perform the matrix multiply, then load another batch, then perform the matrix multiply, then load another batch, then perform the matrix multiply, right? So you're doing that 8 times total because you can only do one at a time. That's where this 8 times comes from. But here with these tensor cores, right, you have 8 of these tensor cores, so you can do all 8 at the same time. So rather than having to do the 34 and then the 4 8 times, you just have to do the 34 once, and then you do the 1 cycle. So it's all at the same time. So you're basically saving doing this 34 plus, here 34 plus 4 8 times, and here it's just 34 plus 1 time. And that's how you get 235 cycles. So you went to basically twice as fast by parallelizing the actual going into the L1 cache, the shared memory, and then the actual multiplication here. Tensor cores reduce the cost of both shared memory access and the multiply and accumulate, which is the add. With the new Hooper and ADA architectures, we additionally have the Tensor Memory Accelerator, TMA, which can accelerate this operation further. Okay, so it seems like more recent versions of the GPUs, right? RTX 40 series, I think this is, so 3090, the GPU that I have here is the generation right before this, I think. Right, NVIDIA 4090 would be part of this ADA series, and then I guess Hooper is like probably the like boring AWS data center version of this consumer series here. But it seems like they have an additional chip or little hardware piece inside this 40 series GPU called a TMA that probably reduces this here. Probably might reduce the 200 cycles spent on global memory. I assume that'll probably be a little bit faster now. Or actually here you go. He explains what it's going to do. Okay, so the TMA unit allows the loading of global memory into shared memory without using up the precious thread resources. Okay, so it's basically going to get rid of this, or kind of reduce this 200. So using the tensor cores, we basically sped up this part of the process, right? The 8 times the 34, and then the 8 times 4 just became 34 and 1. But now, really, at the end of the day, this is really the slowest part here, right? It's 200 cycles spent loading from the global memory. So the TMA is going to try to reduce this here, which is actually where you're spending most of your time. Okay, so threads can focus on work between shared memory while the TMA performs asynchronous. Okay, so basically, while this is going on here, the TMA will kind of start working on this. Once the data arrives, the TMA fetches the next block of data asynchronously from global memory. Okay, so because the TMA allows you to do this global memory step at the same time as this actual multiply and add step, that means that rather than spending 200 cycles for each loading from global memory to the shared memory, it actually only spends 200 minus 34 minus 1. So it's basically, while you're doing it, it's loading the one for the next one, which means that you can reduce this 200 to 164. So now we've gone from without tensor cores 504 cycles, with tensor cores 235 cycles, and then with the TMA 165 cycles. So a total of 200 cycles. So another 15% improvement in speed. Since global memory is by far the largest cycle cost for matrix multiplication with tensor cores, we would have even faster GPUs if the global memory latency would be reduced. We can do this by either increasing the clock frequency of the memory, right, more cycles per second, but also more heat and higher energy requirements. So this is an important thing to realize too, is that a lot of times with these hardware systems, like it's not the actual, like, there isn't any limitation on the hardware itself to run it faster, right? You could actually run it at a faster rate, and people have been doing this with their CPUs for a very long time, right? They do what's called overclocking, where they increase the speed of the CPU. But the problem is that basically when you do that, your little CPU, your little chips in your GPU, they're gonna produce more heat and higher energy. And this will, over time, that little chip will kind of degrade quicker because it's drawing more power, it's producing more heat, it's kind of like warping and damaging the materials in that chip faster. So when people overclock their CPU, for example, they have to basically install a liquid cooling system or a much more aftermarket cooler on their CPU. So yeah, it's just something to think about there. Memory bandwidth. Okay. Seen that tensor cores are very fast, so fast in fact that they are idle most of the time as they are waiting for memory to arrive from memory. During GPT-3 size training, which uses huge matrices, the larger the better for tensor cores. So when they were training GPT-3, the utilization of those cores was at 50%, basically, right? Which means that the tensor cores are only working when they're doing this part of the cycle, right? So they're only working in these 35 cycles here. But for 165 cycles, they're just sitting there waiting for this, for the memory to get there. So your tensor cores are just mostly just sitting there waiting for the memory to grab everything they need, and then they perform their little multiplies and adds, and then they're just sitting there waiting for the next batch to come in. So even right now, right, with the best possible people optimizing the best possible GPUs to train the most advanced, largest model that they can, we're still like grossly underutilizing our tensor cores, right? They're really only actually performing operations 50% of the time. When comparing two GPUs with tensor cores, one of the single best indicators of each GPU's performance will be their memory bandwidth. For example, the A100, which is a GPU that we see all the time in our papers when we read them. This is kind of a popular GPU in research because it's available in clouds environments. A100 has 1,500 gigabytes per second of memory bandwidth, and the V100 is 900 gigabytes per second. So the A100 versus V100 speed up here is roughly 2 times faster because of that. Okay, so that's an idea about bandwidth. I guess the next section here, L2 cache, shared memory, L1 cache, and registers. So here in these earlier examples, there was basically just the global memory and then the shared memory, but there's actually a finer resolution to that. There's actually levels to the shared memory, right? L2 cache, the shared memory, the L1 cache, and the amount of registers used are all related. To understand how a memory hierarchy, right, and this is the hierarchy here, L2 is further away than the L1, helps to understand how matrix multiplication. To perform matrix multiplication, we exploit the memory hierarchy of a GPU that goes from slow global memory to faster L2 memory, to fast local shared memory, to lightning fast registers. So registers are the fastest type of kind of memory, or right at the end of the day, these are tiny little silicone atoms, right? Like little tiny pieces of metal. You want to think of it in your head that have either a charge or no charge, and that's what a bit is, right? It's basically either 0 or 1, and all digital computers, which is basically everything, is based around this idea that you can basically store a value of either 1 or 0. And all of these are basically that. It's just a little area, a 2D area in a tiny little section of a chip that has a bunch of these little zeros and ones stored, right? So the registers are the ones that are closest, most available to the tensor cores. L1 is the next level from that hierarchy, then L2 is the next level from that hierarchy, and then global memory is the highest level. While logically L2 and L1 memory are the same, L2 cache is larger, and thus the average physical distance needed first to achieve a cache is larger. You can see the L1 and L2 caches as organized warehouses where you want to retrieve an item. You know where the item is, but to go there takes on average much longer for the larger warehouse. This is the essential difference between L1 and L2 caches. Okay. So basically, L1 caches are smaller and L2 caches are larger, and because L2 caches are larger, it's going to take longer to go and get stuff from that. I like this warehouse analogy. That made it easy for me to understand. We perform matrix multiplication across these smaller tiles in local shared memory that is fast and close to streaming multiprocessor. Basically just the equivalent of the CPU core, which is the actual the component that's actually doing the actual operation. Tensor cores, we go a step further. We take each tile and load a part of the tiles into the matrix memory tile in L2 cache is 3 to 5 times faster than global GPU memory, which is your GPU RAM. Shared memory is 7 to 10 times faster than the global GPU memory. And then the tensor core registers are 200 times faster. Okay, so here we're talking about basically the memory hierarchy, right? And you have this trade-off between smaller memory, smaller groups of memory are going to be faster, right? The small warehouse. Larger groups of memory are going to be slower. So your slowest group of memory, which is your global memory, which is your GPU RAM. So whenever you actually go and you, I don't know, say like an A100 GPU, right? They're going to tell you 80 gigabytes, right? So 80 gigabytes is actually the global cache, right? So that's the global GPU memory, which is actually the slowest. The L2 cache is 3 to 5 times faster than that. The shared memory is, which is the L1, is 7 to 10 times faster than that. And then the actual registers, which are the closest ones to the actual cores, are 200 times faster. So 2 orders of magnitude of speed difference between the different memory hierarchies here. In fact, you can see TPUs as having a very, very large tiles for each. As such, TPUs can reuse more memory with each transfer from global memory, which makes them a bit more efficient. Okay. Each tile size is determined by how much memory we have per streaming processor and how much we have L2 cache across all of the streaming processors. Okay, so these are different series. So here's the actual series that I have, the RTX 30 series. Turing is the series before that, right? So 2070s, your 2080s, and then The newest generation, the 4090s, is Ada. So you can see the difference in cache here. So it actually, the shared memory is roughly the same. It hasn't changed much over the years, right? 128 kilobytes, 128 kilobytes, which is, it's tiny, right? Kilobytes compared to gigabytes here. But look at the size of the L2 cache, right? The L2 cache from the 20 and 30 series, right? So this is like the 2010s, basically, late 2010s. You're talking about 5 megabytes, 6 megabytes, 6 megabytes. Those are all basically the same. And now suddenly with the 40s series, your L2 cache is now huge, 72 megabytes. That's a 10x over the previous one. Ada has a much larger L2 cache, which reduces global memory access. Or BERT, large during training. So BERT is a large language model, and then these foundational models, right, they come in different sizes. So there's like a BERT tiny, a BERT medium. BERT large is the largest BERT, although there's probably a BERT XL. The input and weight matrix of any matrix fit neatly into the L2 cache of Ada. As such, data needs to be loaded from global memory only once and when data is available through the L2 cache. Yeah, so this fit neatly into the L2 cache of Ada. I think this is important to realize too, is that when you're designing these models, right, if you actually want to be as efficient as possible, you can design them better if you know what you're going to be training them on, right? If you know what the size of the different memory caches are on the GPUs that you're going to be training this, you can design the size of the different layers within that neural net such that they fit perfectly into the specific GPU, right? So that's a little trick that you can. For larger models, the speedups are slower during training, but certain sweet spots exist which make certain models faster. Inference, which is, right, you do your training and you've trained your model, you've pushed gradients into your model. Now you have basically a bunch of numbers in a tensor, and you want to actually do something in the real world with that model, and that's what's called inference. You're no longer pushing gradients into this model, you're just putting input into it, multiplying the weights that you've learned, and then getting the output. And inference is performed usually in batches, right? Because the whole point of GPUs is that you can do things in parallel faster, right? So when you're training, you can train on a whole batch of data, and that'll be faster than training on one individual data point at a time, right? Significantly faster. That's the whole point of the GPU. Inference is also like that, right? You'd like to be able to perform inference batches at a time, but it's tricky because, you know, there isn't going to be a perfect batch of people requesting an inference from this model at the same time. So there's kind of a game that you play there when you perform model inference and model serving, right? Which is actually providing a model for people to like perform inference on, where you want to wait to fill up the batch so that you can perform the inference, kind of do less inferences, but you also don't want to have the user waiting. So there's this kind of like trade-off of like, how long am I waiting to fill up this batch for my inference versus do I just perform inference every time someone sends a request? And this is something where, like, you know, ChatGPT, there's probably some clever stuff going on there, right? Where like they batch the inference calls and they trade off with speed and like how that even just where that inference is being performed can get pretty complicated. But unfortunately for us, I don't think OpenAI is going to tell you that. I don't think they're going to give you any idea. They're never going to really publish how they're performing batched inference to reduce computational cost. Hello, Segi. Hello. Okay. So estimating ADA Hopper deep learning performance. All right, so ADA Hopper is just the latest series of GPUs, right? Practical. Okay. Suppose we have an estimate for one GPU of a GPU architecture like Hopper, Ada, Ampere, Turing, or Volta. Easy to extrapolate these results to other GPUs in the same series. Luckily, NVIDIA already benchmarked tasks. Okay, so these are benchmarks provided by NVIDIA. MLPerf is machine learning performance, so it's like a benchmark for, you have here a ResNet implemented in MXNet. You have here BERT implemented in PyTorch, right? This is a language model. Mask RCNN, this is a segmentation model, so a vision model. TensorFlow MiniGo, I assume this is reinforcement learning. You have here time to train, so I guess this is, what does this mean? Time to, so basically rather than maybe rather than benchmarking based on like how many batches per second, you're basically benchmarking in how long did it take to train a ResNet 50 implemented in MXNet to a 75% classification score. And these benchmarks here, these aren't on consumer GPUs. So this isn't a consumer, this isn't like a machine with one GPU. This is a server rack. This is a server rack that has 8 GPUs. So sometimes when you think about GPUs, you're thinking about in your head like a PC, like a gaming PC that you would have, but that's not what these guys are doing. These are server racks. This is what a server rack looks like, right? In these server racks, you have usually 8 GPUs. You see here, there's 8 of these GPUs here, right? In your computer at home, you probably just have 1 of these GPUs. So these benchmarks here, in this server rack here, whatever this is, DGX H100, they have 8 of these H100 cards in there. So this is not like something that you could do at home. These are like enterprise training systems. Yeah, like look at this. This is crazy. This DGX H100 server has 32 GPUs in it. 72 A100s. Holy crap. What is this? Azure ND? Like, is that has to be like a closet. Yeah, that's huge. Like, I can't even, like 72 A100s. That's like the size of a car, basically. Holy shit, look at this. 1,792 A100s. That is insane. An A100 is already like... Yeah, an A100 is $14,000. So $14,000 times 1,792. That is a $25 million computer. So this computer here is $21,000 or $25 million. Holy shit. So there you go. For $25 million, you can train a mini Go reinforcement learning algorithm implemented in TensorFlow or in 16 minutes. There you go. That's fucking crazy. Okay. Unfortunately, NVIDIA made sure that these numbers are not directly comparable by using different batch sizes and numbers of GPUs whenever possible to favor results. So in a sense, the benchmark numbers are partially honest, partially marketing numbers. Yeah, they're going to pick the numbers that they like the best. You can scale the data center GPU in two ways. One, account for the differences, or account for the differences in 1 versus 8. Yeah, so at home, you're going to be training on one GPU, but in these benchmarks, kind of as we're seeing, these are like server benchmarks. And in these servers, you have 8 GPUs, right? These server racks have 8 GPUs. So looking at the benchmarks that NVIDIA provides, NVIDIA's providing those benchmarks for cloud enterprise people, right? People who want to build data centers and who are looking to drop millions of dollars on a data center. So to them, they care about these 8 GPU benchmarks, the server benchmarks. But if you're just a researcher working in your house, you don't care about those benchmarks because you're only really ever going to have one GPU, maybe 2. Want to come on the stream? All right. As we parallelize networks across more GPUs, we lose performance due to some networking overhead. So the 8 times A100, so the server rack with 8 A100s. I mean, like, this is not super relevant for you guys, right? Like, at this point, they're talking about, like, the cables that connect, basically, these server racks, and you want the fastest possible stuff there. Okay. In the past, NVIDIA sneaked unannounced performance into the gaming RTX. Okay, this is interesting. These are the ones that we use. Decreased Tensor core utilization, gaming fans for cooling, and disabled peer-to-peer. Okay. So, I mean, this isn't good, right? Because as NVIDIA grows as a company, right, most of the money that they make is not actually from consumers. It's not from people like me and you guys buying GPUs for gaming and for local training of deep network. Like, they're really making their money from selling these giant server racks to big customers, right? So when they're looking at, like, okay, what are we going to improve for the next generation of GPUs, more and more they're going to be biased towards data centers, right? They're not going to try to make this the best possible GPU for a consumer. They're going to make it the best possible GPU for these server racks in a data center. So this is a good point that, like, kind of over time, we're likely going to see consumer GPUs, right, or gaming GPUs are actually going to kind of get worse almost. Of course, they're going to get better, but they're not going to get better to the degree that the technology is getting better. Advantages and problems for the 40 and the 30 series. So this is your 3090, your 3070, your 3060. Sparse network training and inference. So sparse here basically means that sometimes when you're when you have your neural net, right, and you've been training this neural net, and you start to you actually look at the parameters of your neural net, right, the weights and the biases. You start realizing that a lot of those numbers in that weight matrix and in that bias matrix are starting to get very close to zero, right? They're starting to be very tiny. And then you start asking yourself, I wonder if I just zero those out, rather than being 0.00001, I just make them 0 instead. And if I do that, can I make training and inference faster? And that's basically the core idea behind sparsity, is that a lot of these neural networks, you can basically remove a lot of the values in those weight matrices and those bias matrices and still get roughly the same performance. So sparsity is the kind of field of research, I guess, and the technique that is a family of techniques that is used to basically prune a network down to only a few or a subset or a sparse amount of weights. And again, we saw how one of the best ways, or an easy way to make a GPU or a CPU more performant, right, is you can basically overclock it, increase the clock speed, but then that's going to draw more power and it's going to create more heat. So it seems like maybe the RTX 40 series, they kind of cranked that up a little bit too much, and people were having issues with this. I heard about people buying 4090s and then it melted their power cables, and basically that's kind of NVIDIA here flying a little bit too close to the sun, and kind of like there's some spec somewhere that says, okay, what's the maximum amount of power and heat that you can kind of realistically pull from a consumer power supply, and they kind of went a little bit too close to that, which meant that the people that had their power supply wasn't as great, they kind of got hosed, and they connected their cable and it just melted. So an important thing to do here, if you're thinking about buying a GPU or deep learning or for gaming on your computer, make sure you get a good power supply, right? Don't use a crap power supply. Buy like a really big boy power supply. So like gaming PC power supplies. Yeah. So don't buy this one. Don't buy this like 850 watt eco, like none of that nonsense. Buy this one here. 1000 watt gold fully power monster power supply. Because not only will it kind of allow you to use the GPUs now, but the GPUs are only going to get more and more power hungry. So by buying a high quality power supply with more than enough power for your system, you're guaranteeing that in the future, when you upgrade your GPU, that your power supply will be able to handle it. Okay, sparse multiplication. So this is kind of what I was explaining, where this is kind of the weight matrix inside a neural net, right? So a neural net is basically just a matrix of numbers, and those numbers kind of encode whatever you've trained in it. And a lot of times, the majority of that matrix is basically just very close to zero. So it seems like the Ampere series has some clever stuff here, which automatically compresses the sparse matrix into a dense representation that is half the size. So it's basically it's clever about knowing that a bunch of these are zero in order to do everything faster, 2x speed up. See how, so it takes this here, where normally you'd have a bunch of zeros, and then it just compresses it into this smaller matrix here. So Tim actually worked in Sparse Network training, and he wrote a blog post about sparse training. One criticism of my work is you reduce the flops required for the network, but it does not yield speedups because GPUs cannot do fast sparse matrix multiplication. Okay. So maybe what he's saying here is that because GPUs are now capable of kind of leveraging sparse matrix multiplication and actually making it faster, that there's an incentive here to actually make your neural net as sparse as possible, right? Take the extra step to make it sparse, right? And do this pruning. Pruning is what they call the process of removing connections. Which is good. I think so basically fitting bigger models into smaller amounts of parameters. Low precision computation. Okay, so this is get a little complicated. So maybe not. Maybe we skip this. But basically, when you store like a float or some kind of number, right? into bits, right? So bits are the kind of zeros and ones that are the fundamental unit of information in a digital computer. The way you store them is actually, there's like kind of a lot there, right? Like people will actually store it as a number with a exponent, right? And then how many bits you use to store the exponent, how many bits you use to store the mantissa, which is basically the part that you're going to exponent after that, the sign, so whether it's negative or positive, like there's all this kind of crap that you can do there, but that's not really going to help you answer the question of deep learning, so we're just going to skip that. Okay, fan design and GPU temperature issues. The new fan design of the RTX 30 performs very well to cool the GPU. Different fan designs of non-founder editions might be more problematic. If your GPU heats up beyond 80 degrees C, it will throttle itself and slow down its computational speed and power. So you can actually, I think they put it in NVIDIA SMI. So if you actually go to NVIDIA SMI, they'll tell you what the temperature is. So we can see that our GPU is 65 degrees Celsius right now. It's actually quite, or not quite cold, but it's not super hot, right? 80 degrees Celsius is the cutoff. Once you start getting beyond 80, it'll start throttling itself. Overheating can happen if you stack multiple GPUs next to together. So one thing you can do is spreading with PCIe extenders. And I use this setup with great success. It does not look pretty, but it keeps your GPU. It has been running for no problems with 4 years now. So this is a gaming PC, and you have a RTX 2080 here. So you have 1, 2, 3, 4 GPUs inside this machine. That's kind of the maximum amount of GPUs you could probably fit into a consumer machine. And you can see that PCIe is basically the part of the motherboard that actually connects to your GPU here. It's what's actually kind of like bringing the memory in. So this part here. And you can see here how he's used these PCIe expanders to put the GPUs further away from each other, right? And by putting them further away from each other, they can cool more efficiently, right? So if you had all 4 of these GPUs just all jammed in here and it was 1, 2, 3, 4, like right on top of each other, the fans wouldn't be able to really work properly and the GPUs would very quickly heat up and then they would throttle themselves. So by using PCIe extenders, he puts the GPUs further away from each other and thus they're able to cool more efficiently and thus they don't ever throttle themselves. So that's quite a nice little hack that this guy has. I think the better idea here would just have multiple computers with 1 GPU each. I think computers are cheap enough that that's cheaper, but I don't know, cool little trick. You can actually see here, so this is the power supply here, this cable here, and you can see how it's actually coming out here. So he's actually removed the power supply. The power supply for this computer is not even in this case. It's like sitting here on the side. And if you actually look at like a Ethereum mining rig, right? So Ethereum is like a cryptocurrency that's famously mined with GPUs, right? So you see here, the guy's got a power supply right there, and then he's got his mining GPUs. He's got 1, 2, 3, 4, 5, 6 of them, and all 6 of them are separated. You see how separated they are? So they're nice and separated so that all of them can cool. And then he's got 2 different power supplies. Actually, look at that. He's got 1 power supply there and then 1 power supply there. And then that's the motherboard right there. So the motherboard has, it looks like 6 PCIe slots. And then each of those blue cables there are basically the PCIe extenders, I guess. So that's the same kind of idea here, but applied to a cryptocurrency mining. So the RTX 3090 and 4090 are 3-slot GPUs, so one will not be able to use it in a 4x setup. Yeah, so the 3090 and the 3090 is huge. It's like the biggest GPU I've ever owned, and it's a brick, and it's very difficult to fit anything else into your PC if you have a 3090 in there. Yeah, and then he talks about here, right? The GPU, this 3080, is going to consume 350 watts, right? And this power supply that we were looking at here, right, the expensive one, this one is only 1,000 watts. So this power supply is 1,000 watts, but 4 cards, 4 GPUs, each consuming 350 watts is 14,000 watts, or 1,400 watts, or 1,800 watts if you have a 4090. So yeah, you have to. This is kind of what I was saying. Pick a really big power supply, because if you have multiple GPUs, it's going to get. They're very power hungry, and they're going to consume powers. So here he's basically. I don't think 4 GPUs in a single computer is a good idea. I kind of disagree with this. Like a 4x 3090 build just seems needlessly intense. I'd rather have 4 computers with a 3090 in them each, or 2 computers with 2 3090s. I don't think cramming that many GPUs into a single computer makes sense to me. Power limiting. Possible to set a power limit on your GPUs, so you should be able to programmatically set the power limit to 300 watts instead of the standard 350 watts. Okay, so here he's basically saying, okay, if you're having power issues, and one thing you can do is you can basically throttle the GPUs yourself. But again, that kind of seems like why are you going to buy a 3090 and then throttle limit it? So here you can actually see this number here, 260 watt, 250 watt, 260 watt, 250 watt, that's the actual power limit. So if I look at my GPU, 350 watt, it's not power limited. My GPU can consume up to 350 watts if it wanted to. Right now it's consuming 174 watts. So this is the power consumption of the CPU. So this is the power consumption here. This is the temperature, and this is the memory utilization. So out of 24 gigs of global cache, as we learned, it's only using 2. You might ask, doesn't this slow down the GPU? Yes, but the question is by how much? I benchmark a 4X 2080 Ti under different power limits, and I benchmark the time for 500. I chose BERT large inference since from my experience, this is the deep learning model that stresses the GPU most. Okay, so here he put power limits on his 4x GPU system with 4 GPUs, and he limited the power to 250 all the way to 125, and you can see how actually limiting to 250 didn't actually decrease the performance, right? Where performance is how long it's taking to do mini batches of BERT large, where BERT is a large language model basically. And he actually power limited all the way to 125, and at 125 you do get quite significant slowdown. Now you're at 26% slowdown. Okay, RTX 4090s and melting power connectors. There was a misconception that RTX 4090 power cables melt because they were bent. However, it was found that only 0.1% of users had this problem, and the problem occurred due to user error. Main problem is that cables were not inserted correctly. Okay, so here's some good advice on making the cables connected well. Use the power connector and stick it to the socket until you hear a click. Wiggle the power cable left to right. There should be no gap. Okay, so click in your power cables. I feel like that should be pretty standard. 8-bit float support. Okay, so an 8-bit float, right? We were talking about floats are just numbers again, and float 32 is kind of what most people are familiar with. You're using 32 bits to store a float, which is basically just a number with a decimals. 8-bit float is a float, which is a number with decimals that basically only takes 8 bits. So rather than spending 32 bits to store the value of this number, you're spending 8 bits to store the value of this number. So this is sometimes called quantization. So when you're training neural nets, you can basically reduce the amount of memory that you're spending to store all the individual numbers. And going from even just 32 to 16, right, you're going to half the amount of memory. So there's a lot of kind of juice to squeeze out of this lemon. And I think the kind of standard now is this 8-bit float data type when it comes to training neural nets. This is interesting. With FP8 tensors, floating point 8 tensors, you get 0.66 petaflops of compute from an RTX 4090. This is more flops than the entirety of the world's fastest supercomputer in the year 2007. A 4x 4090 rig with FP8 compute rivals the fastest supercomputer in the world in 2010. I think that's important to remember, is that even just in 10 years, like, the fastest supercomputer in the world was probably millions and millions of dollars, right? And you can probably, for less than $50,000, make the world's fastest supercomputer 2010 in your house. Okay, so there are some issues with these lower precision data types. Transformers can get very unstable and crash during training or generate nonsense. Okay, so here you have 8-bit and then 16-bit, and then LLM int8, which I guess is like another type of 8-bit that is somehow the method that I developed, LLM.int8, can perform int8 matrix multiplication with the same results as the 16. Okay, so he's kind of selling his stuff where he figured out a way to basically store 16 bits into 8 bits, which is roughly what this chart is telling me. Because if you use these compressed data types, right, this 8-bit here, eventually you get to a point where it just doesn't work well. FP8 data type is much more stable than the int8 type, and it's easy to use in functions like layer norm or nonlinear functions, which are difficult to do with integers. I think this will make FP8 training and inference relatively common. Okay, so layer norm is layer normalizations. It's a kind of like regularization that people will put in between the layers of their neural net. So in between each kind of layer of neurons, or after a convolution or something like that, you'll have these like layer norm operations, and it sounds like people would always use higher precision data types for these, but it seems like FP8 data type can actually use it. So seems like FP8 is just going to become the standard. And shit, there's even FP4 now. Okay, that's cool. 4-bit inference. That's crazy. So we went from 32 bits to 16 bits 8 bits now to 4 bits. Below, we see a chart of the raw relative performance across all GPUs. Yeah, so I mean, this is, you see here the ADA series, so the 40 series. You can actually take advantage of the 8-bit inference versus like in a 3090 here, or in the 30 series and the 20 series, the 8-bit inference, 16-bit inference is basically the same. So, I mean, maybe that's another thing, right? If you're thinking about buying a GPU, if you are more interested in kind of hardware and performance and kind of throughput, like this guy here, Tim Dettmers, like he's all about that. If that's something that you're interested in, getting a 4090 and the 40 series would actually probably be better for you because it allows you to play with that, right? You can actually see a difference between 8-bit inference and 8-bit training and 16-bit, right? Versus if you're more interested in different parts of the deep learning pipeline, then, and you're never really going to use 8-bit inference, then it doesn't really matter. Yeah. Okay, GPU deep learning performance per dollar. Okay. So below we see the chart for performance per US dollar for all GPUs sorted by 8-bit inference performance. Okay, so he's saying you need at least 12 gigabytes for image, 24 gigabytes for transformers. I mean, I don't know. I don't know. I think this is really rough because like there's huge image models, and a lot of image models such as the Vision Transformer are transformer based as well. So he's more thinking about like image generation as in like how he says basically you need 12 gigabytes to run Stable Diffusion, 24 gigabytes to run Chat GPT or whatever the version he's using. $4070 is the most cost effective. There you go. RTX 3080 remains the most cost effective. So if you want it, the answer, if you've been listening to this whole long stream, is a RTX 3080. That's the answer right there. Get an RTX 3080. Best GPUs for academic and startup servers, so this is now server GPUs, is A6000 Ada GPUs. The H100 SXM is also very cost effective. If I would build a small cluster for a company or academic lab, I would use 60% A600 GPUs and 20% H100 GPUs. Yeah, so here's the performance per dollar. So he has them ranked here, and like the 3080 10 gigs is the most cost effective. This is the one that I have, the 3090 24 gigs. I think it's not about cost efficiency to me. I think like the actual amount of memory is huge. Like, so to me, like having 24 gigs is more important than being slightly faster and slightly cheaper. Like, I think having the big GPU memory is important. Here is a recommendation flowchart. Okay. So you start here. Are you in an organization? No. Am I doing training? No. Am I doing inference on large language models? No. Then choose an RTX 4070 or RTX 4080. You want something cheaper? An RTX 2080. You want something cheaper? An RTX 3060. You want something even cheaper for small or streaming data sets? Yes, Lambda Cloud. Yeah, so cloud solutions are actually probably the best MO. If you want to do local training and you're interested in GPUs and like building a system and you like computers and kind of getting your hands dirty, then yeah, make your own rig and buy your GPU and think about it and kind of think of it as a hobby project. But if you're more interested in just deep learning and the software side of it, you don't need to buy a GPU. Just go to a website, go to some of these cloud services like AWS, of course, or Lambda Cloud, or any of these kind of like hosted cloud services, and you can just rent the GPUs per hour. And that'll be easier. You don't ever have to deal with buying things and gluing them together and all that crap. So here you go. You know how in our papers we always see the A100s? That's if you're rich. If you're training huge models, right, greater than 13 billion parameters, and you're rich, the A100 is king. Keep them by the next GPU, the future of GPUs. In the past, it was possible to shrink the size of transistors to improve the speed of a processor. This is coming to an end now. Moore's law is dead, as some people have said, but I think there's interesting counter arguments against it. While shrinking SRAM increased its speed, this is no longer the case. Current improvements in SRAM do not improve its performance anymore and might even be GPU RAM still increases in speed if we stack memory modules, but these are expensive to manufacture. The main way to improve the speed of a GPU is to use more power and more cooling. Yeah, so basically they stopped being able to just add more transistors. So what they started doing is they basically just started overclocking their GPUs, right? Make the cooling more fans, more heat sinks, better heat sinks, and then just kind of overclock them. But there's kind of a limit to that, and you can see that they're getting they're already at that limit because a bunch of people who bought the 40 series like melted their power cable, so they can't really do that again for the 50 series that will eventually come out. Chiplets. Chiplets are small chips that are fused together with a high-speed on-chip network. You can think of them as two GPUs that are so physically close together that you can almost consider them a single big GPU. AMD has a lot of experience with chiplet designs. AMD's next generation GPUs are going to be chiplet designs, while NVIDIA currently has no public plans for these. This may mean that the next generation of AMD GPUs might be better in terms of cost performance compared to NVIDIA. Okay, the main performance boost is specialized logic, right? So specialized hardware. We will see widespread adoption of 8-bit inference and training in the next months, right? Especially as we have the 40 series. We will see widespread 4-bit inference in the next year. Currently, the technology for 4-bit training does not exist, but research looks promising, and I expect the first high-performance floating point 4 large language model with competitive predictive performance to be trained in 1 time. Yeah, so the GPUs aren't getting faster, but we're getting better at compressing the models. So, right, you go from 16 to 8-bit, half the size. 8-bit to 4-bit, half the size again. So the models are just, you're going to fit. The models are the same size model is just going to get smaller. And that's how you're going to get the inference speed higher. Going to 2-bit precision currently looks impossible. Yeah, I don't know how that makes sense. I don't even know how 4-bit makes sense, right? It's like 4-bit is literally just 4 zeros and 0 and 1s, right? Like 2-bit, you literally just have 1 0. You have 0 0, 0 1, 1 0, and 1 1. Like, how the fuck can you represent anything in that? We'll probably be able to improve the combination of algorithms and hardware to the year 2032, but after that we will hit the end of GPU improvements similar to smartphones. Yeah, so we're kind of on the plateau here. The wave of performance improvements after 2032 will come from better networking algorithms or like crazy shit like optical computing and quantum computers, right? That could kind of be the next way that we achieve 10x in scale and then 10x over that. It is uncertain if consumer GPUs will be relevant at this point. It might be that you need an RTX 9090 to run super hyper stable diffusion ultra plus 9000 extra or open chat GPT 5.0. I think this is the future. Some company will offer a high quality API that is cheaper than the electricity cost for an RTX 9090. Yeah. So I think the time of buying a GPU and putting it in your computer and using it, like, that time is coming to an end. And even for gaming, right? Like, people are like, okay, well, I'm not going to be training models on my computer, but I want a GPU so that I can game. And I think that maybe that will also disappear. And you saw, for example, Google Stadia, right? This idea that actually the game is running on a GPU in some cloud server somewhere, and you don't own the GPU, you don't own the hardware, you're just basically streaming it like a Netflix show, right? So to me, I think cloud computing is where this all ends, right? Is that basically consumer GPUs and having actual hardware in your house goes away. And especially another thing to consider here is VR, right? Where if you get to the point in VR where you have, I don't know, 5G internet or 5G cell phone service, 6G cell phone service, 7G cell phone service, and the latency keeps getting better and better and better, right? You're never going to have a GPU in your house. You're just going to have the screen that's connected to 6G internet. Can I use multiple GPUs of different GPU types? You cannot parallelize efficiency across GPU types, so you will go to the speed of the slowest GPU. So if you're going to have multiple GPUs in your computer, don't put one that's crappy and then one that's fast. NVLink is not useful. NVLink is a high-speed interconnect between. Useful if you have a GPU cluster with 120. Buy used GPUs. I use GPUs without polluting the environment. I think this is like nonsense. Like, I'm just gonna be honest. Like, people who say that GPUs cause carbon, like, your washing machine is producing carbon, your electricity is producing carbon, like, there's so many other things in your lifestyle that are producing way more carbon than the GPUs in your computer. But $50 gigabit network card if you want to parallelize across 2 machines. Do I need an Intel CPU to power a multi-GPU setup? I do not recommend Intel CPUs unless you heavily use CPUs in Kaggle competitions. Even for Kaggle competitions, AMD CPUs are still great though. AMD CPUs are cheaper and better than Intel CPUs in general for deep learning. For a 4x GPU built, my go-to CPU would be a Threadripper. Okay, so there you go. This guy recommends Threadripper CPUs. Does computer case design matter for cooling? No. GPUs are usually perfectly cooled if there is at least a small gap between the GPUs. Right, so we look at our Ethereum mining rig, right? That's probably more than enough gap that you need. Basically, you don't want the GPUs like right on top of each other where like the fans aren't pulling anything. Will AMD GPUs ever catch up with NVIDIA GPUs? No. Don't buy AMD GPUs. Crash. AMD is kind of like Julia versus Python, yeah. Agreed. Python is way better. Julia's crap. Yeah, this is to me, I think, the most important thing about cloud versus local is that you can scale. Right? It's very easy to scale up and scale down. Versus like if you have a GPU at your home, it's almost impossible to scale up and scale down, right? You're gonna have to buy more. You're like very quickly gonna turn your house into a server farm, and you're gonna spend your time just like fixing GPUs, which you don't want to be doing. Versus if you use cloud, you can just scale up, use more, and use less. So here's a little calculation that he does for an AWS V100 spot instance and compared to the price of a desktop with a single RTX 3090. So a desktop with a 3090 cost around $2,000. Fine. And then in the US, the price of electricity is roughly $12 per kilowatt hour. So if you have 350 watt, which is what the GPU is using, with 100 watt your GPU or your CPU, you're using it roughly 15% of the time of the entire year, right? 24 hours and 365 days. You're spending $71 on electricity. The break-even point for a desktop versus a cloud instance is 15% utilization. So if you use your GPU more than 15% of all the hours in the day, then it's potentially worth making your own 3090. But this doesn't factor in the cost in time of building your own computer. Cool. So that's the end of this. Yeah, so the best GPU for deep learning, after reading this, a 3080 or a 4070. But cloud computers are better. So that was which GPU to get for deep learning, or the best GPU for deep learning. This is a blog post out of Tim Dettmers here. Really awesome researcher who is very good at hardware. So go ahead, check out his stuff. And thanks for listening.